Yeah, thanks for the introduction, and thank you all for being here on the final day of this what has been a very nice conference. So I'm going to talk to you about this morning online learning of quantum processes. And yeah, this is joint work with my collaborators Asad Raza, Matthias Caro, and Jan Zeisert. And here you also have the archive number. Okay, so before I get to the setting of online learning, I thought perhaps to first describe to you the usual setting of online learning or the usual setting of machine learning, which you might all be a little bit more familiar with. So the usual setting of machine learning is as follows, and this is also referred to as supervised learning, right? So you start with some labeled training data, right? So you have some data which has been labeled, and you use this to develop some model, right? And then the model is then used for prediction on some test data, right? So this is the kind of usual setting of supervised learning that you might all be familiar with. And the point is that this has a distinct training and test phase. All of the data is given to you in a batch, right? And, and in particular, sometimes there are some mathematical assumptions about the data being distributed in an IID fashion, right? And then the goal here is to obtain good generalization on your test data, right? And this is the kind of thing that's analyzed within the framework of this of PAC learning or PAC, probably approximately correct framework of learning. Right. So this is the setting that you're probably all familiar with. But now we want to consider a setting in which the data isn't all given to you in a batch. Instead, it's given to you sequentially, right? And we also might want to relax assumptions like the data being distributed in an IID fashion, because this might not necessarily be realistic. You might also want to be in a setting where you want to update your hypothesis as the data comes in, right? So this is the kind of setting that online learning is meant to achieve or meant to help with, right? So here in the online learning setting, this is how it proceeds, right? So you have some source of your data, and then you have a learner, right? So at any particular time step, you're going to be given some data, right? And on this data, you need to come up with some prediction, right? So your current prediction at time step t might be this function f, right? So then you output to the source f of t. Right? And then as a consequence of your choice, as a consequence of your current model of the hypothesis, you will incur some loss, right? And this loss will essentially be the difference between what you guess and the actual label, right? So the source might give back to you either the label itself or a loss, right? So sometimes this differs depending on what you read, right? And this kind of procedure just goes on sequentially in this manner, right? And in this case, the way we evaluate the learner is not through a notion of generalization per se, but through this concept of a regret, right? So either the number of mistakes or the regret or both, right? So here what we want to actually look at is doing this for some number of time steps, call it capital T. And among those time steps, you essentially look at the total loss that you incurred over those T time steps, right? And then from this, you subtract away the loss that you would have achieved had you had all of the data to look at once, right? So sometimes people will look at this quantity as the difference in the loss in hindsight, right? Because the second term here in this function RT, which we call the regret, is the minimum loss that you would have achieved had you had all the data to look at once, right? So you would have had the opportunity to select a function from some class having seen all of the data, right? And this is called a regret because it's kind of like after this whole thing has been done, you find out what you could have achieved. And so maybe you want to minimize that, and it's kind of called a regret for that reason, okay? And these loss functions are the kind of usual things that you might expect, like an absolute value loss or like the squared loss, okay? And in the case of online learning, the way we characterize the performance of the learner is through, so it's through the regret, but in particular, we want to achieve what's called sublinear regret, right? So what this specifically means is that this regret, if you look at the average regret, so this R of t divided by t, in the limit of an infinite number of rounds, you want this kind of to converge to 0, okay? So what this means is that you want the regret to scale sublinearly with respect to this capital T, okay? So this is essentially the goal in online learning. And there's one very prominent algorithm that can achieve this, and this is called matrix multiplicative weights. And I'm going to describe this algorithm within the context of a prior work on online learning of quantum states, because I think it's quite helpful to think of it within this context. So the setting of this problem is as follows, right? So we essentially want to estimate expectation values of a state, right, with respect to some observables. So that's the general setting, but now we want to do this in an online or sequential manner, right? So the ways this goes is there's a source which gives you measurement operators, E, right, at any given time step. And from this, we have access to the unknown quantum state in terms of being able to do a measurement with respect to this observable, right? And once we do a measurement with respect to this observable, we get some estimate, right, which is called S of t, okay? So this would happen just by doing measurements on that state, which is unknown, right? And this will incur some loss. So at the same time, as you do this measurement, you actually have internally a guess for what your state actually is, right? And this is what we refer to as omega, right? So you have this guess of what your state should be, and at the same time, you are estimating by taking expectation values or by doing the measurement of that observable what you believe to be the expectation value. Look at the difference between those two, and that's essentially your loss, right? And based on this loss, you'll again update your guess for the state. Okay, so this is a setting of online learning of quantum states, and an algorithm that achieves sublinear regret in this setting is known as matrix multiplicative weights, right? So importantly, this achieves sublinear regret in the sense of having this order of square root of t scaling of the regret. And the algorithm essentially, it proceeds as follows, right? So you start from an initial guess of the maximally mixed state. So that's W of 1. So W1, you normalize it. And then the loss, so here I describe it in a more general way where instead of just some kind of scalar loss, you could have a matrix that describes the loss, right? So you receive the cost or the loss matrix, and then you use this to update according to some learning rate, which is referred to here as eta. Right? So depending on how high your loss is, you might want to actually tend towards keeping your current estimate or using the loss to update your estimate, right? And the rate at which you do this, that kind of trade-off between keeping the current estimate and updating it based on the loss is what is referred to here as the learning rate, denoted by eta, okay? And the result, and this is actually just purely in the classical sort of online learning literature, right? So a priori, this has nothing to do with learning quantum states. But as was shown here in this paper of Scott Aronson and others, it can be applied to learn quantum states in this kind of setting, okay? And in particular, the sublinear regret, so the regret here is given by the expression that we have here, right? So these terms here are your losses, right? So there's the sum of the losses, and here you have the loss in hindsight, essentially, right, for any quantum state rho, right? So then you could also minimize over that. So there are two important things here. One is the fact that you can get sublinear regret by choosing eta in a particular way, in particular choosing it in this way. Another interesting thing here is the fact that here d is the dimension. Okay, so d is the dimension, and here what we see in the regret that it's the dimension dependence is like logarithmic, right? So if your dimension is 2 to the n, which is what you would have for quantum states, then here you only see a linear dependence in n, and with respect to the number of qubits. Right, so this is kind of interesting, right? So now we might want to ask ourselves the question, what happens in the case of quantum processes, right? So this is the thing that we're actually concerned about here in this work, right? So in the case of learning quantum processes, first of all, we should ask ourselves, what does it mean to take expectation values of a quantum channel, right? So in the case of quantum states, it was pretty easy. I mean, we just think about it in terms of some measurement or some Hermitian operator more generally, right? But now in the case of a quantum channel, you have some extra degrees of freedom, right? In particular, you have the extra degree of freedom of some input state that you can feed into the channel, right? So you can input a state rho into the channel, which is unknown, so I represent it by this kind of blue shaded thing. So it comes out, and then you do a measurement at the output, right? So that's kind of your expectation value. It's kind of this combination of an input state and an output measurement, okay? And what we can do is we can write this expectation value in terms of what's called the Choi matrix of the channel, right? So the Choi matrix is essentially just the channel applied to 1/2 of the unnormalized maximally entangled state, right? And the fact that it's actually the unnormalized maximally entangled state is kind of important because of the fact that this equality here, that second equality, right? Which basically tells you that you can think of the expectation value as just some operator multiplied by the Choi matrix, and you take the trace of that. So it kind of looks like the expectation value of an observable with the state, except now we replace a state with the Choi matrix. So the normalization condition kind of changes. Okay. And now we want to do basically the same thing, right? So now we want to look at a setting where, yeah, actually, and more generally, you can have an observable which is more general than just an input state and output measurement, right? In particular, you could have a reference system or an auxiliary system for your input state. You apply the channel only to one half, and then you do a joint measurement, right? So these are more general, what I would like to call channel observables. Okay. And now in this setting, we want to do essentially the same thing, right? So this diagram here on the right-hand side is just kind of copied over from the previous slide, but now with respect to quantum states, right? Or channels, right? So what we now want to do is estimate these observables. We have a source that gives us an observable. We do the measurement, and then we output an estimate, right? And now we want to achieve essentially sublinear regret, right? But we don't just want to achieve sublinear regret, right? So to some extent, sublinear regret will be clear just by applying known online learning algorithms. But here we demand also something that comes out kind of for free in the state case, which is the fact that we want the regret to scale sort of polylog in D, where D is the input dimension of the channel. Okay, so this is something additionally we demand in addition to the sublinear regret. Okay, and what's nice about this setting is we can actually extend the setting of this problem to processes which are not just quantum channels, but more generally multi-time processes or non-Markovian processes, right? So what we can more generally do is consider a diagram at like what's shown here at the top, where you might have still a quantum channel, but you might have three uses of a quantum channel, right? And then observables on three uses of quantum channels are what sometimes are referred to as testers, right? So this tester consists of an input state followed by these adaptive operations, which I'm calling D, and then finally at the end a measurement. Right? More generally, you can have, yeah, and in this case, the expectation value will still have the kind of form that you would want because it's basically just the Born rule, right? So the Born rule for quantum states, which we all know from quantum mechanics, generalizes also to processes, right? And that's essentially why we get this kind of structure with the trace of some operator that describes the tester times the Choi matrix of the process. And for basically the same reason, our process, which is depicted in blue, could also be a non-Markovian process with the non-Markovianity coming from the fact that you have some memory here, right? And so what's nice about this setting is that it can be used to describe learning processes of this kind as well, right? And it doesn't come with much additional like overhead in terms of the mathematics, right? It just the fact that the Born rule generalizes to arbitrary processes. Okay. So now our goal, instead of outputting a sequence of quantum states, is outputting a sequence of Choi matrices, right? So we want to achieve low regret in the sense of sublinear in the number of steps and also polylog in D. Okay. So that's the setting of the problem. And now, before I actually get to the results, I wanted to also talk about the fact that having described the setting, you might be thinking, okay, why don't we just learn the Choi state, right? So we have an algorithm that can learn quantum states, so why don't we just apply that to learn the Choi state, right? So the reason why learning the Choi state won't give us exactly what we want is the fact that when we actually take the expectation value, we actually get the Choi matrix instead. So it's like the trace of E times the Choi matrix and not the Choi state, right? So if we actually wanted to rewrite this in terms of the Choi state, then here for this expectation value, we would actually get a factor of D here, right? So if this D is exponential, right? So if you have n qubit system, then D is going to be 2 to the n, right? So we could apply essentially the known algorithms, for example, the matrix multiplicative weights algorithm to the Choi state, but then we would achieve sublinear regret, but we would not achieve the other goal that we had in mind, which was this polylog D scaling regret. Right? So this we would not get. And the subtlety essentially is, yeah. And another point which I forgot to mention is that while known algorithms for states, the updates for the states only need to have trace 1, but we have this additional constraint for choice states, which is that the reduced state should be maximally mixed. So this can actually be dealt with pretty easily by doing a projection step, which I won't really get into. But we'll still have the problem of this exponential scaling of the regret with respect to d, or to the number of qubits. Okay. Yeah. So the point is that our task is to learn the Choi matrix instead. Okay. All right. So now let me get to some of the results. Okay. So here, let's go through this a little bit slowly. So here we have results that achieve what we want for certain classes of channels. Okay, so as you might maybe think already, it's not really possible to do both of what we want for arbitrary channels, and we in fact prove this as well, right? So we can show exponential mistake and regret bounds for arbitrary channels, and this comes about just by embedding the sort of task of learning Boolean functions into our task. These ones are known to have exponentially scaling regret, and so we will inherit the same results for arbitrary quantum channels. Okay, so this basically tells us that we need to look for what we want by restricting the classes of channels in some way. Okay, and so the way we did it was to look at these channels, which are called what we call G-gate channels. So these are channels composed as a sequence of at most G 2-qubit channels. It's kind of a generalization of like a circuit model where you might have a circuit composed of some number of 2-qubit gates and maybe like a brickwork architecture or something like that. But now for the case of channels. Okay. And the way we prove our mistake and regret bounds in this setting, and here capital L that's appearing in these bounds is the Lipschitz constant of the loss function. So the way we get the proof here is we apply known regret bounds in terms of sequential covering numbers. So there are known bounds in online learning in terms of sequential covering numbers based on the concept class that you want to learn. And by bounding the covering numbers corresponding to this set of channels, we can get regret bounds for this class of channels. Okay. So another class of channels for which we can achieve the kind of regret that we want is what are known as, for Pauli channels, right? So so for Pauli channels, so here we have to, and also in the case of the G-gate channels, we have to assume a priori that we have some knowledge of what the channel is, right? And so there are some aspects of the channel that we just don't know, right? In particular, in the case of Pauli channels, we somehow know that the channel is a Pauli channel, but we don't know the error rate vector, that probability distribution, right? So Pauli channels have Krauss operators which are proportional to the Pauli operators, and all we need to know are those the scaling factor, which is just some probability. So here we can actually just apply the known MMW algorithm to learn this Pauli error rate vector, right? So this is one case where we can actually just apply the known classical algorithm. Okay. And what's nice about this particular technique is that we can actually extend this result to arbitrary convex combinations of known channels, right? So if we have a convex combination of some set of channels which we somehow know, so if there's a promise that our channel, our unknown channel is just a convex combination of some channels, but we just don't know the distribution of the convex combination, then we can learn that distribution using the MMW algorithm. Okay. And I won't get into it just for the sake of time, but we also have results on like computational complexity lower bounds. Okay, so for the remaining time, I actually wanted to talk a little bit more about this MMW algorithm, because we have an MMW algorithm for quantum states. And so we asked ourselves the question, which we couldn't really answer, is could we have an MMW algorithm for quantum channels along with some guarantees on the regret bound, right? So we know already that in general for arbitrary channels, we're not going to be able to achieve what we want in terms of like a regret bound which scales polylog in the number of qubits. But we could ask ourselves, could we still achieve sublinear regret, or could we have some analog of the MMW algorithm that still converges? And so the way we are thinking about this now is using the following fact, right? So here's just the MMW algorithm that I presented before, right? What's interesting about this algorithm is that it can be written as the following optimization problem, okay? So this update rule that you see here essentially comes from doing a kind of maximum entropy optimization, okay? And in particular, it comes through this particular optimization. So at every step, you want to update your quantum state in the following way, right? So here, D is the relative entropy. Rho is the thing that you're optimizing over, and omega t is your current guess, right? Omega t is your current guess, S is your current estimate, right? And so now you can actually prove, and it's shown in these references, that this update rule of the MMW algorithm occurs from this particular optimization problem, right? This is nice because it gives us a path towards a similar framework of MMW, but instead for tailored really directly to quantum channels, right? So now we can ask, yes, and we can also see here, so this is our update rule, which is just over there, but now we can see how this loss matrix actually relates to the loss function that we have, right? So the update will be directly characterized by how big this difference is. If this difference is small, then it won't really impact the update, and the update will instead just be closer to the original state. Okay, and eta characterizes how much weight is given to this distribution or to this difference. Okay, so now we can do the same thing for quantum channels, right? So we can kind of just sort of copy over the optimization problem, right? And so we can say that now our task, this kind of sequential task, if m is our current estimate of the quantum channel at time step t, right? And we have this difference, right? This is our loss, right? And this is our estimate of the expectation value, this particular expectation value, right? For that observable, right? Then we just want to solve this optimization problem over all quantum channels, or in other words, CPTP maps, right? So one question that arises here is how do we actually, what is the entropy or like relative entropy of a quantum channel, right? Or between two quantum channels, what's the relative entropy, right? So here we quantify that. It's commonly quantified in terms of like a worst case over all possible inputs, right? So you take the maximum over all possible inputs to get it, right? And so now I'm going to have a little bit of an advertisement of some work that has been recently coming out that we put out recently on this. So we started looking at this kind of problem in this paper. And we can actually solve this optimization problem in the most general case, right? But what we haven't yet done, and which is still the direction for future work, is to prove convergence, right? So this algorithm here for quantum states, depending on the value of eta that you pick, the learning rate, you can prove that it converges to the true state, right, as you increase the number of iterations. But it turns out that it seems to be much more complicated to do this in the channel case, primarily because of the fact that the relative entropy has this form for quantum channels. So what I've, so with this oh, what happened? Oh, okay. So I'll just conclude now by, so here in the previous slide, it was a little bit speculative on a new kind of formulation of MMW with some progress, which you can find in that paper. So what I've talked about here is an online learning framework for learning quantum channels, extending the framework for quantum states. And one of the crucial points that I wanted to sort of convey, which I hope became clear, is that this goes beyond just learning the choice state, especially if we demand regret bounds, which are scaling sort of polylog in the number of qubits. On top of that, one of the key messages here is that in general, this just won't be possible, and that you have to somehow restrict the classes of channels in some way, right? And the way we did that in our paper was to look at Pauli channels and what we call these G-gate Pauli channels, or G-gate channels, okay? And a future direction which I'm kind of interested in is proving convergence of this channel-based MMW algorithm that I just briefly presented, right? So this seems tricky because one of the tools in proving, for those who might already know, one of the key tools in proving the convergence of the MMW algorithm for quantum states is the fact that the channel, or is that the relative entropy for states is a Bregman divergence. But this seems to maybe not be the case for quantum channels, or at least it's not known to us. Right? So one of the questions might be related to that. And even if it's not, it could be very well that it converges, which we see in our paper here. It seems to converge, but we just don't have a proof of that, and maybe the proof technique will be completely different. And to me, that's kind of interesting, that possibility. And with that, I'll just leave it there. Thanks.
Thank you, Sumit. We'll take questions now.
Yeah.
Thank you so much for the talk. I have a few questions regarding actually the approach that you've taken. So, like the data that you've been passing is sequential and not in batches. So, I understand that it was like a good way to approach the online learning. So, what if we can send the data in batches? Can like other algorithms can be used in that aspect, like machine learning, other machine learning algorithms in that aspect. And my second question is if we use some other machine learning algorithms in this aspect, will there if is there any other parameters in which we can evaluate this other than the regret that you have mentioned in this talk?
Okay, so I think I didn't catch your first question. What was the first question?
The data that you have been sending isn't sequential, right? And
Yes, it's
not
sequential.
in
Yeah.
batches. So like if you can use do it in batches, can we use other algorithms and also get like compare the work of yours with these algorithms as well?
Yeah, so I think there are papers which kind of combine this kind of sequential and batch learning, sort of like a hybrid. So I think you can. Yeah. Yeah. And sorry, what was your second question?
It was so if we can do it in batches, so
Yeah.
is it like the regret is the only parameter to evaluate, or we can like evaluate in other parameters as well?
Yeah, that's a good question. So I think, as far as I know, yeah, regret is commonly used, and also the number of mistakes. Um, but I think one of the issues could be that, yeah, I mean, you want some kind of objective function or some way to evaluate this that you can actually work with. So this is one kind of setting which is kind of reasonable, like with the regret, it's kind of reasonable, and also you can prove something about it. But I think it's a good question to think about what other figures of merit that you can consider in this online setting.
Thank you so much.
Mhm.
Yeah, thank you. So my question is about the observables that you want to learn on. I'm here.
Oh, okay.
Yes, on choice states, on choice matrices. Sorry, if you restrict it to just input states and the measurements, so if you have this tensor product structure with respect to input output
Yes.
subsystems, does it make it easier or harder for you?
It doesn't make it, no, neither actually. So here we don't need to make any assumptions on the specific form of the observables, just the fact that they are indeed observables.
Yeah, but if you would restrict, would maybe you could extend to other channels, maybe.
Mm, possibly, but I'm not sure how. Um, so the way we do this, it's, yeah, at least using the techniques we did, it's not clear that this would happen, at least not immediately clear to me.
Okay, thanks.
Thank you for the great talk. In your MMW algorithm, in each step, you minimize channel divergence with respect to CPTP constraints.
Mhm.
Could you explain more about whether if there is a efficient way of let's say polynomial time way of doing this, or how can we
Right.
minimize
So
this? Yes.
you mean like to, for example, solve it numerically?
Yes. Yeah. Let's say yes.
Yeah. So yeah, so there are ways of, for example, relaxing this, which we kind of explore in our paper over there, using STPs. So there are STP bounds or semi-definite programming bounds for the relative entropy that you can use to get bounds on this.
Like using hierarchy or
Yeah, hierarchical
yes.
bounds.
Yeah.
Yes.
Thank you very much.
Yeah. Mhm.
Thank you for the talk. I wanted to know, minimize this. So instead of the usual relative entropy, if you choose any relative entropy or some such thing, do you think it would help in proving convergence?
Yeah, this is a good question. So it could very well help. So and admittedly, it's not something we have like fully explored. So I think there are good reasons for choosing the usual sort of von Neumann relative entropy, due to like, yeah, physics reasons, I guess. But if we just replace, for example, this this relative entropy, this channel relative entropy with some alpha Renyi entropy, then it's a good question whether this would help in the convergence. And we did try a little bit, but it was still not entirely obvious. Yeah.
Thank you.